Okay. Okay, so let's say you want to FOIL 3 plus 4i raised to the fifth power. What I mean by that is you're doing 3 plus 4i, 3 plus 4i, 3 plus 4i, 3 plus 4i, 3 plus 4i. You're doing it 5 times. Do it twice. I'm sure you guys could do it by hand just fine. It's not a problem. In fact, actually, I think it'd be 9 plus 24i plus 16i squared, which comes -7 plus 24i, I think. However, this can get very time consuming. We have so many to do. So we need a better approach. So this is kind of, to be honest, this is the true reason why mathematicians somehow discovered, hey, we can convert this to a trigonometric form and have a more efficient way for expanding this. So for example, let's say z equals r cosine theta plus I sine theta. So if you're going to do z squared, I mean, I know it's going to look like this, right? R cos theta plus I sine theta times another one, right? R cos theta plus I sine theta. I think it's pretty obvious, right? Now, if you were to clean it up, I'm not going to go through the process, but if you were to clean it up, actually, no, we did do this. We did this derivation actually the other day, right? When we were doing this up here. Remember we did that proof? And remember there's a double angle involved, right? So we did do it. But if you go through the motions again, you get this. R squared, of course, right? And then you have cosine 2 theta. I'll put 2 theta in parentheses. Plus I sine 2 theta. Hope you guys can see that. Actually, I'll put it down below. Ah. Okay, now for z cubed theta, sorry, for z cubed, we gathered that's the same thing as z squared times z, right? Or you could do this. R squared cos 2 theta plus I sine 2 theta times, let me erase the other stuff because it's getting a little messy now, times z, which is r. Hey, Jackson. I just know we skipped homework review. We're just going straight to notes right now. Sorry. Okay, if you were to work that out, you would get this. You just have to just trust me. This is what happens. But if you were to kind of go through the motions and use identities, combine stuff correctly, you wind up getting this. Now, for Z4, I'm not going to work it out. I'm just going to just tell you what it is. Z4 is going to be this. What do you think is going to be cosine what? Yeah, there's a pattern, obviously, right? And we won't waste time with Z5. I think you get the point. So what does this mean? This means that from raising Z to the n power, it's simply going to be R to the n bracket cosine and theta plus I sine and theta. Cool. Makes sense. So this is called Demois theorem. So guessing it's a French mathematician. My French is not very good, but I think I pronounced it right. Demois theorem states that if z equals that, and you raise it to a power, then you're just going to get this, r to the n. I know I'm repeating myself. Bracket cosine and theta plus I sine and theta. I'm going to give this formula, don't worry. So the test, just so you know, is going to be non-calc the entire test. So no calculator. Whatever. However, I am going to give you guys formulas, just so you know. You will get formulas. Yep.
So if you want to give us like a bearing problem,
If I give you a bearing problem, it'll be something that you can easily compute. What was that? Yes, with unit circle, exactly. Right. So I'll probably blank unit circle. I'll do that. No, yeah, I'm not gonna do like, oh yeah, bearing of like 305 degree, like not that crazy. It's gonna be something you guys can handle. And I'll ask you to leave it in exact form. So don't worry about that. Yeah, actually, I'll do that. Have to happen later this morning. So I'll put in Schoology. I'll put an update. I'll email you guys as well when it's ready. You definitely have the conics one, but there's other ones too, right? The parametric ones, you kind of need to gather how that works. So I'm not going to necessarily do that because you would need to know, like, oh, if x equals this sine theta or this cos theta, whatever, that you kind of need to figure out. But but this stuff for sure, definitely, I'll do that. Vector stuff was pretty straightforward. I don't think you guys really need that. I mean, you guys should know the length of a vector. It's Pythagorean theorem, right? You guys should know that. I don't need to give that to you guys. Yeah, but this stuff, of course, this is weird stuff. So I'll give that to you. And of course, all the conics as well. And the foci, c squared equals a squared plus b squared, a squared minus b squared, all that fun stuff. So let's do an example right now, just to see how this works. So yeah, now one thing you could do, just so you know, for those who are taking the Ethan, I know some of you guys already taken the ACT, and you're well, and I know you thanked me for so you said you saw the ellipse problem. That's good. That's good. Sometimes they put imaginary number problems too. I've seen that on the ACT. Like with I, whatever. And I know you guys can deal with imaginary numbers just fine, but just so you know, the graphing calculator does compute imaginary numbers for you. It's actually really nice. Not sure if you know where it is. So if you're taking the ACT again, or if your software haven't taken it yet, you're going to take the ACT. I haven't really seen this on the SAT so much as the imaginary numbers, but if it's second decimal point, that's what an imaginary number is. So for example, the problem that we're just about to do is asking for this. Well, I could just punch it in. It'll give you the answer. It's lovely. Root 3 raised to the third power. And boom, there you go. It's -8. It's nice. One thing you might need to do is go to mode and switch that to A plus switch it to A plus BI. Because sometimes if there's an imaginary number, it might not show it. So well, let's say I mix this up and change that to the 4 power. So you'll give that. And you're like, well, that just looks really nasty. Can I change that? Sometimes you could. If you go math, frac. Sometimes it'll change to a fraction for you. Unfortunately, it does not. Unless you have the TI Inspire, like a more sophisticated calculator, then it would actually give you the radical form. But yeah, just so you know, it's there in the calculator. Say, go ahead. How do you get to what? Sorry? That's what we want. We want that. No, that's what this is giving right now. Yeah, we want that. Oh, it gave you -8 plus 0i. What? When you did the problem I just did right now? 1 plus no. Raised to the third power? Oh, okay. I knew you did. All right, let's keep moving, guys. All right, here we go. So let's do this problem right now. So really simple. Let's figure out R. So R is going to be root A squared plus B squared. Don't forget that, right? Which would be root 1 plus 3, root 4, which is 2. So it's 2 bracket cosine of 3 times blank plus I times sine of 3 times blank. So how do I find theta? What's theta going to be, guys? Tan theta is what? It's a B over A, right? Which happens where in the unit circle? So you have to know your unit circle well. Good, pi over 3. It's the first quadrant. 2 to the third. Yeah, do I put 3 for n?
No, just like the.
Oh, you're right. Sorry. Yes. Yes. My bad. My apologies. Yes, you're correct. Thank you. I forgot about that. So it's cosine pi. What's cosine pi? Yep. And what's sine pi? And that's why you get -8. There you go. What's sine pi?
The I.
Yeah, what's sine pi?
Oh, zero.
What's 0 times I? 0. By the way, this is kind of interesting. It's going to be what the next topic we're going to talk about in just a few minutes. So you get -8, right? What's the cube root of -8? There are more cube roots. That has to be a cube root. Think about it. What if I just do 4 cubes? I mean, I know you can do that. That's 64. And what if we go backwards? Cube root of 64 is 4. So this is interesting. -8. You guys have not been told the whole story. Yes, cube root of -8 is -2 as a real number. So as an imaginary number or a complex number, there are more roots of -8, not just -2. In fact, actually, there are 3 different roots. We'll talk about that. This will blow your mind when we get there. Because think about it, that has to work, right? If I cubed 1 plus I root 3 and got -8, the cube of -8 has to be 1 plus I root 3, as well as 1 minus I root 3, I think. And of course, -2. We're going to go over that in just a moment.
If it was not plus 0, we would just include I in that.
Exactly, right, correct, right. Exactly. So do the same thing here, guys. I want you guys to do this on your own. Solve for R. Solve for theta. Then work it out. Okay, I'm going to freeze the screen and work it out. Let's see if we get the same thing.
Theta equals B over A. Oh, let me show you. Tan
So,
theta equals B over A or A over B?
B over A because you need Y over X. Opposite over adjacent. Because in a complex plane, remember, the imaginary is Y, the real is X. So you have to rise over run. Or sorry, opposite over adjacent. Sorry. Which is kind of the same thing, I guess, but go ahead.
And would B equal to sine, like would be the sine equivalent?
Exactly. Yes. Yes. Okay, it's in the second quadrant, right, guys? So it should be 3 pi over 4 for angle.
Why can't it be like 7 versus 7 5?
Because we're not in the fourth quadrant, we're in the third quadrant. Because think about the complex plane. We have a complex plane. The real number is X, the imaginary is Y. So your X is negative, your Y is positive.
Oh,
Well, X negative Y is probably happy in the second quadrant.
wait, what's I root 2 over 2?
So think graphically what's happening. But good question, though. Definitely want to ask that.
Oh, well, that would be negative. You put the R to 0.
How many rotations is that?
Oh, Mr. I don't want.
Yeah, go ahead.
Oh, it's A plus BI, and we do R of A squared, square root of A squared plus B squared.
Correct.
Not B squared. Okay.
Well, no, it's A squared plus B because because you're trying to find the absolute, you're trying to find the absolute value. Of course, yeah. No, you have to, because you want the distance. It's yeah, correct. No. Right.
I isn't part of B. B is
Right,
just
right,
above
it's B,
B.
not.
Okay, here we go, guys. Here's what I got. So one thing I am kind of doing, it's kind of not, well, it is intentional, I suppose. But I'm kind of forcing you to really circle well. Because, yeah, you gotta know that, obviously. And then you have to 55 4 inch, but okay, I'm almost doing 2 full revolutions, almost 4 pi. There's 1 revolution plus 7 pi before. So yeah, you gotta figure out you're in the 4th quadrant. Because when you're doing AP calculus and you're doing a lot of trick stuff, you're gonna have to know your unit circle like that really fast. So it's gotta be quick. So yeah, know your unit circle well. Okay, all's good. Nope. Okay, we'll take some time. But we're down to the last part of the notes, which is actually kind of my favorite. And it's a little bit of brain surgery in a way because you have to really be mindful what you're doing. Rocket science, not quite rocket science, but yeah, we got 2 examples and they're pretty lengthy. Okay, we're good. All right. Okay, this next one kind of recalls the fundamental theorem of algebra. So if you think about something that's fundamental algebra, it's like, okay, well, that just seems, kind of crazy, right? Because you've been doing so much stuff up to now. Like, why all of a sudden you guys are just so close to calculus? Why we're bringing the fundamental theorem of algebra? Well, it's always good to talk about the fundamentals, right? Like, we know, for example, if you have a polynomial, like, don't write this down, by the way, but if you have a polynomial function, right, like x to the n power plus dot dot dot, right, you kind of expect there'll be n roots, right? Like if I had x to the 4 power, there probably should be 4x intercepts, right? And actually there'll be 3 turning points. Or if I had x to the 5th power, I probably have 5 roots. Now some of the roots might be imaginary, might be irrational or whatever. But the bottom line is, regardless if it's real or not real, the degree always equals number of roots. That's the fundamental theorem of algebra. Okay. Even if you may not even see that graphically because of imaginary solutions. So in this case here, if you have x is 6 equals 1, someone would just think, oh, it's just x equals 1, and that's it, right? They just think, yeah, that's x equals 1. Sorry, I can't even do an arrow today. Oh, I'm struggling. Sorry, x equals 1, or plus or minus 1, maybe they might say that. But here's the deal. It actually has, okay, I need a new mouse or something, or a stylus, my bad. It actually has 6 solutions. And, if you were to go to Desmos, like, sure, let's go to Desmos right now. And let me graph y equals x to the 6th power. Or sorry, minus 1, my bad. Yeah, I mean, clearly there are 2 answers, right? There are really 6 answers. 4 of them are hidden. And you guys remember doing this back in the day? Actually, we will review this later on. But you guys remember like doing following rational roots? Did you guys do that in Mr. Band's class? You guys didn't do synthetic division? You did? You guys remember that? And you remember he had to find like all the different solutions? You guys didn't do that? I got to talk to him. Okay, maybe okay. Well, bottom line is there's a process you would use to find all the zeros by doing polynomial division. We're not there yet. We'll talk about that in the spring. But the bottom line is that there's other solutions, not just 2. There's actually 6 solutions. 4 of them are hidden, and they're imaginary. Let's find them. That's what we're gonna do right now. We're gonna find them. Okay. So one thing you could do, you can think of like this, right? Isn't that a true statement I'm writing right now? Right? What factoring technique that I just performed right here? Difference of 2 squares. And there's also something called difference of 2 cubes. I could break it down further like this. Do you guys talk about difference of 2 cubes? Okay, I'm going to blame CPM on this because CPM actually, I think, failed you guys on this part. Yeah, because I teach CPM algebra too. I don't think they do this either. Well, so that's called That's called difference or sum of two cubes. Makes sense, right? Okay. Well, I should say makes sense. Anyway, that's what it is. So of course, what does this give me? X equals 1, right? What does this give me? X equals -1. This will give me two imaginary solutions. You can work out if you want to, but I know you guys do quad forms, so not too worried about that. This will also give me two imaginary solutions. So there has to be 6 answers, right? Because if I break it down like this, which I know you guys have seen, if you break down further, which you may not have seen, I don't know. This is called difference of cubes, sum of cubes. And then realize, oh, well, that's x equals 1, that's x equals -1, and that's a case of quadratic. That actually, I think it's -1 plus minus I root 3 over 2, if I'm not mistaken. I think this is a 1 plus minus I root 3 over 2, I think, if you were to work it out. But sometimes we may not have that luxury of breaking down the polynomial this way, or it might be just hard to do. So we want to process a little more streamlined, that's more organized. And that's what we're going to talk about next, which is kind of an extension of de Moivre's theorem. It's called find nth root of a complex number. And it looks like this. I definitely have to give this to you guys because I tend to forget it. We don't teach this in Precalculus. We don't do this at all. Pre-cal AB honors, maybe, I don't know. I did teach this pre-cal AB honors pre-pandemic when we had a lot more time. But if I'm not teaching this class, trust me, I forgot this. Like 3 years ago, if you asked me, this year, like, what is this? Like, I don't know, I gotta look it up. I forget too, so I'm gonna give this to you guys. It's a little crazy. Here's what's happening. You got a complex number, right? And the nth roots, by the way, if you're gonna find 5 roots, gotta give me 5 answers. 6 root, gotta give 6 answers. You gotta do this 6 times, 10 to 6. So it's an iteration. ZK is the iteration. So K being 0, 1, 2 until you get n minus 1. So for example, first of all, n is 6. You gotta put 6 here. And then R, of course, and we know how to do that. Theta, we know how to do that also. And the way the iteration works is you do 2 pi k when you start k equals 0. You do it again, k equals 1. Do it again, k equals 2. Do it again, k equals 3. Do it again, k equals 4. Do it again, k equals 5. Until you've exhausted all the options. Until you've gone the number of roots you need. So 6. And of course, n is going to be 6 here, right? So yeah, seems a little confusing. Let me show you an example. It's not that bad. It's actually an incredibly organized approach, but you got to be highly organized, by the way. So if you're having a hard time keeping organized, talk to me. I'll work with you because you got to really stay organized about this. Zaid first and then Thomas, go ahead. 1 and 2. Yeah, you're going to do 3 separate calculations.
So you do 0 plus
0 for k. Everybody else is the same.
So 6, you do 0 through 5, not 1 through 6.
0 through 5, exactly. Yep. Yep. And you'll see why. Actually, once I finish it, I'm going to kind of go a little bit on the deep end using a unit circle. You'll see why we have to do it that way. Why we start with k equals 0. Right now, it's not very obvious. You will see once we get there. So let's revisit x to 6 power equals 1. So when you find the 6 roots of 1, what you're really doing is solving this equation here. Some people call it the 6 roots of unity. We talk about unit circle is raised to 1. We talk about unit vectors has a magnitude of 1. So I think you gather unity kind of deals with 1 in math. So you hear the word unity, think of 1. So 6 roots of unity, right? Okay, great. That's what we gotta do. We gotta find 6 roots of 1. I mean, duh, obviously 1 multiplied by itself 6 times is 1. -1, same thing, is also 1. But they're also imaginary numbers too. And then when we graph them on a complex plane, you'll see why we have to start at k equals 0. Like, why am I starting at k equals 0? How come I start at k equals 1? Like, what is that? Why is that a big deal? You'll see once I finish the problem and put the answers on the unit circle, that'll make more sense. And pun intended, it'll all come full circle. Get it? Unit circle. All right. Fine, I'll stop. Okay, let's go. All right, so ZK. Let me write the formula first. ZK is going to be the nth root of R times bracket cosine fraction theta plus 2 pi k over n plus I times sine theta plus 2 pi k over n. Okay. So we're going to do this 6 times.
That's right.
Yeah, good.
What's the point of adding 2 pi k? Because it's not just not change.
You'll see in a moment. Just let me go through the process. That's what I was saying. Wait till we graph it, it'll all make sense.
Okay.
Yeah.
What is all in this?
Great question. What do you think R is? What's your A value? Think of it like a complex number, guys. 1. What's your B value? And how do you find A? So how do you find R? Which is what? 1. It's just 1. I'll explain. Give me a sec, guys. Just gotta say a little. I gotta streamline this a little bit. Okay, notice I'm kind of getting this all ready, right? Okay. Let's solve for R in the top right corner. So if you have so your complex number is 1 plus 0i. Would you agree with that? 1 plus 0i. So we solve for R. Isn't that square of a squared plus b squared? So what does that equal? Just 1. Let me switch a contrast to that. That's terrible. Let's go crap, hold on.
Is the basic equation for imaginary numbers. It's only going to be 1 plus 0. That's how the formula is. It's the regular.
Anyway, R is 1. Okay. Guys, you guys see what R is 1? Okay. What's a complex number here? Well, what number are we evaluating? We're taking the 6th root of 1.
Yeah.
1 is a complex number. All numbers are complex. Even if it doesn't have I, it's still considered a complex number. What's the A value of 1? What's the B value of 1? Plug into the formula for R. Square of a squared plus b squared.
So there just is no B.
There's no B, right? Obviously there's no B. So square root of 1 squared plus 0 squared, which is what? 1. It's 1. So R is 1. Also graph it on the complex plane. You're graphing 1 comma 0, right? What's the length of that? Just 1. Just 1. R is 1, guys. Okay. I mean, just think about it. What if I had 1 plus root 3 I? That R is 2, right? How did you compute that? You did a squared plus b squared square root, right? What if you have 1 plus 0i? Wouldn't you do the same exact thing? The square of 1 squared plus 0 squared, square rooted, right? That's all. So just 1. So what's your theta going to be then? It's going to be 0. Yeah, think about it. We're on. Actually, I'm going to draw the unit circle now because I said I was going to do it. Might as well do it now. Okay. I'm sorry. These colors suck. I might need to change my contrast again on this. That might be a little better. Yeah, guys, you're right here. That's 1 plus 0i. Right? So it's 1 plus 0i. Okay, yeah. So your theta is 0 also. Okay, your theta is 0 also. All right, now let's go through the motions here. Okay, so you're going to have the 6th root of 1, which I know obviously is 1, times cosine of 0 plus 2 pi times 0 over 6 plus I sine 0 which if you were working out carefully, you should just get 1. Think about it. What's cosine of 0? 1. What's sine of 0? 0. 1 times 1 is 1. So we get that. That's easy.
History.
Yeah.
If like the whole thing is finding like 6 different roots of one, how can you just say it's one?
What do you mean?
Like it's like x to the 6 equals 1, so we're finding like 6 different.
Because we're gonna have because there are complex numbers. When I raise it to the 6th power, gets me 1.
Like at the beginning, it's just 1.
It is, but watch when we do the other scenarios, you'll see there are 4 other roots that are complex numbers with I in them. If I raise them to the 6th power, will actually work out to be 1. So that's the first one. So it's right there. So that's k equals 0. Now, if you think about it, let's do the next one. I know it's gonna be 1 times cosine 0. That's my starting angle. Plus 2 pi times 1 over 6 plus I sine 0 plus 2 pi times 1 over 6. Okay. Now, think about what's happening here. The 2 pi gets divided how many ways, guys? 2 pi gets divided how many ways? 6 ways, right? What's 2 pi over 6 reduced to? What's pi over 3 degrees? 60. How many degrees is full revolution? That's why start k equals 0. Starting here, they do 60, 120, 180, 240, 300. By the time you come to full circle, am I back to where I was started from? That's why we start k equals 0. You do k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, k equals 5, until you've completed 1 full revolution. Granted, we could technically start at k equals 1, go to k equals 6. I guess we could do that and still be fine. So, I mean, I guess they just want to start it at the true starting point, which is 0 or whatever. So that's the reason why we do that. Because what's going to happen, I'm going to have five more answers that complete the full circle. So that's what's happening, is that because also think about it. What's the radius of the circle here? 1, right? And we're doing r equals 1. So what I'm doing is I'm trying to break one down into 6 separate answers. And that's why we break it down this way. Now, if I work this one out, what's cosine of pi over 3? And what's sine of pi over 3? Now, Kyle, to answer your question, if I were to raise that to the 6th power, that will be 1. That will be 1. And I'm just going to go through the motions again. 1, 1, 1, 1, times, brackets, 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 cos, 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 cos. And you see, it just becomes a very kind of organized approach. It's really not that hard to get the formula. It's actually pretty easy. I, times sine, times sine, times sine. Sound like a broken record. Times sine. Bracket, sorry, fraction, fraction, fraction. 6, 6, 6, 6, 6, 6, 6, 6, bracket, 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 equals, 0, 0, 0, 0, 0, 0, 0, 0, plus, 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 plus. And then 2 pi times 2, 2 pi times 3, 2 pi times 4, 2 pi times 5. Sorry, it's going to be really hard to squeeze this in. 2 pi times 2, 2 pi times 3, 2 pi times 4 and 2 pi times 5. Okay. And let me get the all the answers now. That should be what's cosine 2 pi over 3, guys? Negative half. Then this is going to be -1. Then this will be -1/2 again, but minus √3/2. Because you're doing 8 pi over 6 with 4 pi over 3. And then positive 1/2. And there you go. Those are your 6 answers. So that's how you find the roots. So now we know other possibilities for the 6 root of 1, not just 1 and -1, but there's 4 other possibilities are complex, truly complex numbers with an imaginary number connected to it. Yeah.
Like for k equals 0, for r you wrote the 6th root of 1, and then you just wrote that as 1 there.
Yep, exactly.
The whole point is that we can't write
1 or -1, exactly. There's 4 other answers.
how are we like there, we're just writing 6th root of 1 as just 1. How can we get for all the r for like k?
So R's 1. We know that. I understand. What's your question?
Like we're doing all of this to figure out what the sixth root of 1 is.
Yeah, exactly. So what number? Not just thinking about real numbers, also thinking about complex numbers, right? What numbers, when I raise it to the 6th power, gets me 1?
Right, but
That's what I'm trying to figure out.
And then for k equals 1, 2, 3, 4, and 5.
Yeah.
for
So what
r,
I'm trying to find all the. See, what's happening here is that I'm going around the inner circle 6 times. So this is the first one, right? And then what's happening is that I'm doing 2 pi k over n. So 2 pi is 1 revolution, right? So I'm trying to find other places where that could happen. So what's happening here is that the nth roots are equally spaced around the circle, around the inner circle. That's what, because you have 6 root, 3/6 divided by 6 is 60 degrees, or pi over 3. So I'm trying to find other possibilities where this could happen. Let's try one more, guys, and then we'll win the notes. Okay, why don't you guys try example 10? Okay, we're gonna do cube root, so not as bad. Okay. So let's make sure we got r and theta right first. Okay. Let's make sure we got that taken care of.
How do we end up graphing on this page, or how we?
Oh, I don't know why that graph. Don't worry about that actually. We'll do it at the end. It's not that hard. We'll do it at the end. I don't really care about that so much, but. Okay. What's your r, guys? √8 or 2√2. What's your theta? Good. 5 pi over 4. Good. Wait, no, not 5 pi over 4. 3 pi over 4.
Oh yeah.
Okay, good. Okay, to get this kick started. Okay, this is gonna be a little wacky. I would not. So you would need a calculator for this clearly, but we're gonna leave an exact form because you clearly would need a calculator for this. But you're gonna do the 3rd root of 2√2, which is kind of crazy, right? So I wouldn't. What I most likely would do when I write this question is I might say, hey, leave it in an exact form, or I might do it as a multiple choice question, perhaps. So you don't have to worry about the calculator, right? So you could just gravitate towards the answer. So maybe I might design it that way. Okay, cosine. Now this is where you gotta be really, really careful. What are you gonna put in that fraction? Don't tell me. What are we gonna put? Good. 3 pi over 4 plus 0 over 3. And then I sine 3 pi over 4 plus 0 over 3. Okay, so we got that right. That looks good to me right now. Connects up. I'll calculate later. Cosine
We can just write in the line.
Sorry, say again?
Writing. Oh, no.
You can see it gets a little bit messy after a while. Not a terribly fun process. Because unfortunately, I'm gonna have to use a calculator. The first one should be pretty easy though. Let me erase the stuff up top because I don't think we need it anymore now. The first one should be pretty easy. What do you think my first root would be? So it's going to be well, it's still not super easy. It's going to be the cube root of 2 root 2 times cosine of pi over 4. It's not no, it's 3 pi over 12. You're dividing by 3, dude, not multiplying by 3. Yeah, gotta be careful. Yeah, it's a common mistake that people will make. Which would be the cube root of 2 root 2. And what's cosine of pi over 4? Plus root 2 I. And that's kind of crazy. If you go Sean, yeah, go say it. Yeah. Yeah, so think about it. That's a 6 root of 8, right? And isn't 8 2 cubed? Right? And what is that reduced to? Do you guys see what I just did? Okay, so 2 root 2 is so let me back up a little bit here. I know I confused the guys. It's my bad. Does that make sense? Right? Because 2 root 2 is root 8, right? So does that become 8 to the 1/6 power? And what is 8 as a power 2? Isn't that 2 cubed? What does that become? 2 to the 1/2 power, right? Okay, let me back up a little bit here. Okay. Okay, let's back up here. Okay. What's 2 root 2, guys? It's root 8. Okay. It's root 8. You're okay with that, right? Okay, what's root 8? Is it 8 to the 1/2 power? We're okay with that too, right? Okay. What's 8? 2 cubed, right? We're okay with that too. Okay. So it becomes this now. And now if you cube root that becomes 2 to the 1/2 power. Because remember, you got to be very fluid with your radical and fractional notation. That's the point I'm trying to make here. So anyway, that becomes just root 2, really, if you think about it. And if I distribute, I should just get 1/2 plus 1/2 I, right? Sorry. No, sorry, I should get 1 plus 1 I. So it winds up coming all that. If you work it out. I'm not gonna do the second and third ones because those are kind of nasty. I'm gonna leave that alone. Maybe because those are just getting really, really messy. So, and also it would involve using some difference formulas, which I don't want to do right now. So I'll leave that alone. But at least you know the process. That's what I care about. So, Adam, go ahead.
Will we have to know, or will we have to use like sum and difference formulas on the test or?
If I do, the test will take 2 hours. I'm not gonna do that to you guys. Just too much material. It's a lovely problem to do. I might be a great final exam problem, so thank you for the idea, Adam. Just kidding, those right here. Don't worry. Yeah, I know. Adam's coming with great ideas for a final exam. Adam, what do you want to like write the final exam with me during Thanksgiving break? Let's do it together.
Oh, yeah, I should write it.
Okay, yeah, let's go. Yeah, all right. Okay.
I'll write it.
Anyway, no, that'd be a great way. That'd be a great way to combine that skill. But we haven't used that skill in a while, so I don't want to do that to you guys. So, all right, I'm all done.
Put an oval in here.
All right, we only got a few minutes left, so why don't you guys just work on the homework if you want. The test, I'll disclose more details about the test on Tuesday. Okay. So homework, just so you know, is this right here. Hold on, David. So homework will be 7 through 13. Okay. And that's all it is, just 7 through 13. That should be plenty. So just the rest of the homework here. If there are any questions about the homework, just ask. I did put the answers in Schoology. Maybe we could go over all the homework tomorrow. That's fine. And then we'll talk about review and I'll give you guys a review packet. So yeah. All right. I'm gonna stop.
So this is my question from earlier.